I want to talk now about sprinkler system capacity. We need to know the total capacity on a system, obviously, if we're going to be able to design a pump station. And so we need to know some information that is going to be dealing with the consumptive use as we've gone through all of this calculation of evapotranspiration. That's going to dictate our volume per area that we need to apply. So if we look at that as a daily process and find out what our capacity needs to be on a daily process, we have some options to talk about. The first thing is we have to know, are we going to be watering 24 hours a day, 12 hours a day, 8 hours a day? Because that will have an impact. If we're doing agricultural irrigation, more likely than not, we can run the system 24 hours a day. If we're irrigating a playground at a school, we might be restricted to maybe 12 hours a day. If we're irrigating a golf course, we might be dropped clear down to 8 or 9 or 10 hours a day, simply because of the land use. We don't want to be irrigating while people are out using the facility. And so turf again becomes more of a critical player as far as amount of irrigation or time of irrigation and when it can be applied. Now, if we can irrigate 24 hours a day, we only have to have a system that has 1/2 the capacity of a system that would water 12 hours a day. And if the system can only water 8 hours a day, it has to be 3 times bigger than a system that irrigates 24 hours a day. Because we have what we call the water window. It keeps shrinking, but we still have to put the same amount of water on per day. The crop is still going to use its water. It still needs to be replaced. So we have to be able to fill that water profile back up. And it's easiest to look at it on a day-to-day basis like we would have in a turf situation. And again, we're looking at the most critical crop, turf. And so then we can expand that to take it into more days cycle if we would like. But say that we have, and again, it's a mathematical manipulation to get the gallonages. Okay? So if we have a certain amount of water that we have to apply, inches of water on a given piece of turf, for example, on a day, and we have X number of acres, we can go through a mathematical calculation. So let's just plug through one to see what it costs. So let's say that our consumptive use for turf on a given day equaled 0.30 inches. So we have consumed that much and we need to put that much back. Let's say we're on a golf course and it was 100 acres. Let's say our water window equaled 8 hours. Okay, so we're giving ourselves a very concise set of parameters to work from. Now, we need to know how many gallons a minute are we going to be able to run continuous to get this job done if we just can turn this system on and start watering and go right across the course and keep at optimum flow rates. Optimum would mean balancing the flows continuously so we're running the same gallons a minute over the full 8 hours. Now that's going to bounce a little bit up and down because in golf courses it's all valve and head mostly, and so we're turning heads on and off continuously. But if we have a good system, we can get it so that we're staying within about 5% of the given flow rate, plus or minus, all the way through our water window of 8 hours. So these would be our parameters. Now we simply have to do a little mathematical calculations to get ourselves there. Looks pretty easy, doesn't it? Can we do this? Well, let's see what we got. We can convert this to acre inches, can't we? So we know that we take the CU times the area. And that will give us the volume for the day. And so we're going to have 0.30 inches times 100 acres, which will equal, oh, this is per day, inches per day. Make sure we get a time in there. So that's going to be 30, what we call acre inches per day of water.